This video is on Newton's method. Now, the technique for approximating the real zeros of a function is something called Newton's method, and it's basically using the tangent lines to approximate the graph of the function near its x-intercepts. So to see how this works, we want to consider a function f continuous on the interval, the closed interval from a to b, differentiable on that open interval. If fa and f of b differ in sign, then by the intermediate value theorem, the function must have at least one zero on that interval, right? Remember, intermediate value theorem said if we had two x's, an x1 and an x2, and if the y value of one was negative and the y value of the other was positive, then at some point they have to cross the x-axis because it's continuous and differentiable, okay? So to estimate the zero, what we're going to do is we're going to pick some value of x, just an estimate, and we're going to use that point to find where that tangent line crosses the x-axis. We're looking for a new x value, that x2. Now, basically, I know a couple of things, right? I know that we have x1, f of x1, right? We have these they're crossing the x-axis at kind of the same place. That's the kind of the goal, is for these two things to be fairly close to each other, okay? Now, because we can easily calculate the x-intercept of that tangent line, we can use it as a second estimate of the zero of f, okay? So the tangent line passes through the point x1, f of x1, right? That's the point that we picked. We know the slope, right? The slope is just the derivative of that function evaluated at that point, right? x1. So in point slope form, we can rewrite it because we know that the point is this, the slope is the derivative at x1. So remember, the formula for point slope is y minus y1 equals m times x minus x1. So y minus y1, f of x1, equals m, which is that slope, times x minus x1, which is just x1. So if we add f of x1 to both sides, we get y equals f prime times x minus x1 plus f of x1. Now remember, at this point, we're looking for where it crosses the x-axis. So we're looking for when y equals 0. So what we're doing is if we let y be 0, then really we wouldn't even have to have made this leap here. We could ignore this and say that this is 0, right? So if we're looking for a new x, well, we're going to take this and we're going to divide by f prime. So f prime of x1, right? So if you look at this, f of x1 divided by f prime of x1, then we've got x, because this is what we're looking for, x. We've got the x1. So we're going to add x1 to both sides. So we've got x1 minus f of x1 over f prime of x1. So this is actually the Newton's formula. X equals x1 minus f of x1 over f prime of x1. So basically, we pick an x1, plug it in, and we get a new x. So a lot of times you'll see it written as x2 equals this, because this is going to give us the second value of x. And basically, we're going to take this and find an x3 by changing this to x2. We're going to keep plugging it into this formula and do repeated iterations, okay? So this is Newton's method. You just keep doing it until you get the most accurate answer that you're looking for. So if we let f of c equal 0, this is the y value when at c, right? And f is differentiable on the open interval containing c, then to try to approximate that value of c, we start by making an initial estimate, make it close to c. If we have, if we're able to graph it, or if we see a graph, it's helpful to have because we can kind of guess somewhere in that vicinity. Then we're going to determine a new approximation using the form x of n plus 1 equals x sub n minus f of x sub n divided by f prime of x sub n. Now, when we can take two iterations and find their difference and it's within some desired accuracy, then that final x value that we got is going to be our final approximation. Otherwise, we just keep redoing this iterations over and over and over again, okay? So we want to use 3 iterations of Newton's method to approximate a 0 of f of x equals x squared minus 2. Now, we can solve this flat out. We know how to solve this. This is quadratic. I know that my answer is going to be plus or minus root 2. But I'm using this basic one to show you how to do this, okay? So we're going to use x prime. We're going to use x sub 1 equals 1 as our initial guess. So I know that x sub 2 equals x sub 1 minus f of x sub 1 divided by f prime of x sub 1. So what we need to do is we need to know what f prime is, right? So I know that f equals x squared minus 2. F prime equals 2x. So I can figure this out. I can find, okay, I'm going to show you the easiest way to do this. Now that I have this, I'm going to set up a table. Let's make it somewhat accurate. All right. So I've got some value for x. Okay. Now, once I have x, I can solve for f of x. Right? I'm just going to plug that x value into f. Then I'm going to take that x value and plug it into f prime. Then I'm going to do f of x divided by f prime of x. And then lastly, I'm going to do x minus f of x over f prime of x. And I'm going to do this until I get the desired accuracy that I want, or I do the number of iterations that it asked for. So in this problem, it tells us to calculate 3 iterations. So I start with x1, x2, x3, and x4 will give me my 3rd iteration. So my f of x was x squared minus 2. My f prime is 2x. So my first x1, let's do this. We're going to use 1. So I'm going to plug this in. 1 squared is 1, minus 2 is negative 1. 2 times 1 is 2. Now I'm going to divide. Negative 1 divided by 2. It's negative 1/2, right? I don't have to actually do that. And then I'm going to say, okay, x, which was 1, minus negative 1/2, which is 1 plus 1/2, which is 3/2. Or, since I'm doing decimal approximations, I can say 1.5. Now, I'm going to plug 1.5 in here, so I get 1.5 squared minus 2. So I'm going to use my calculator. 1.5 squared minus 2 equals 0.25. Now, 2 times 1.5 is just 3. And then I do 0.25 divided by 3, which is going to give me 0.083. And then I do 1.5 minus 0.083, gives me 1.416 repeating. So I'm going to plug that in. Let's go ahead and square that. Minus 2 gives me 0.0069444, right? If I plug in 1.416666 times 2, that gives me 2.83 repeating. So I'm going to divide the 0.0694 divided by 2.83, and that's going to give me 0.024509.8, blah, blah, blah. So 1.416 minus 0.0024 gives me 1.414215, 1.414215, we'll call it 7. That's my third iteration. That's the solution that I'm looking for. Now, if you want to see this a little cleaner, here are the prettier versions, right? This is going to be a lot of calculator work. If you want to work all these out by hand in terms of writing all of this down, you can, but really you want to keep these values in your calculator because your calculator is not going to round and you're not going to lose anything in terms of rounding errors. So notice 1.414215.7, so they rounded it to 6, so I did it right. Now, in example 1, the approximations approach a limit. Okay, so the more you do it, the more it converges towards that spot. So we call that convergence. Moreover, when the limit is C, it can be shown that C must be a 0 of F. Okay, does that make sense? If the limit is C, if it's converging to C, that has to be a 0. Okay, now Newton's method doesn't always yield a convergent sequence. Sometimes it gives you different things. Take a look at this example, 3.63 here. If I plug in this, I get that the derivative equals 0. Well, because Newton's method relies on dividing by the derivative, if the derivative equals 0, then that's somewhere where it fails. That's something I can't do. I'll get a math error, right? So if you encounter this problem, what you're generally going to do is you're going to pick a different value for x. This generally only happens with your initial guess. It's not going to just randomly happen inside of like the third or fourth iteration. So if it does happen where you get f prime equals 0, just pick another value and keep going, okay? Another way that Newton's method can fall is going to happen here. Fail, not fall. So imagine we have x to the 1/3 power, okay? This function is not differentiable at x equals 0, okay? Now, we want to show that Newton's method fails to converge. And we're going to use 0.1 as our initial guess, okay? So if we take the first derivative, we get 1/3 x to the negative 2/3. All right? Now, we know the iterative formula is x of n plus 1 equals x sub n minus f of xn over f prime xn. Now, this is not something we do all the time. You can do this with some of them, and actually it makes your computations a little bit easier. But I'm going to show you here that if we plug this in, right, if we plug the values of f of x sub n and f prime of x sub n, we get, okay, f of x is just x to the 1/3. We've got the derivative is 1/3 x to the negative 2/3. Well, notice that these are the same variable with exponents. 1/3 minus negative 2/3 is just 3/3, or x to the first power. This 1/3 we can multiply top and bottom by 3. So we wind up getting x sub n minus 3x sub n, which is just negative 2x sub n, which means whatever our guess is, we're just going to multiply it by negative 2 to get to the next guess. And if you look at that, if we go through all, I'm not marking it out, I'm going through these steps. So if I go through all these steps, I wind up with negative 0.2, because all I did was multiply by negative 2. Multiply by negative 2 again, 0.4. Multiply by negative 2 again, negative 0.8. Multiply by negative 2 again, I get 1.6. then I get negative 3.2, then I get positive 6.4. You see how all this is doing is increasing. The absolute value of it is just increasing constantly, right, by a factor of 2. So that means it can never converge. I'm never going to get two values that get, close to each other. This is what's going on here. All right. Basically, x sub n continues to increase in magnitude as n approaches infinity. So no matter how far out I go, this is what happens. I picked x1, it gave me a new x2. Then I picked that, it gave me a new x3. It picked another one, it gives me a new x4. Notice how they're just going further and further out. Okay? So it's never going to converge. So for this one, it fails to converge. It can be shown that a condition sufficient to produce convergence of Newton's method to some 0 of f is that if you multiply the function times the second derivative and divide that by the first derivative squared, if the absolute value of all that is less than 1, then it converges. Okay? I'm not going to make you memorize this. This is just some interesting side note. Okay? If you look at this function, x to the 1/3. So we're talking about x to the 1/3. So f of x equals that. All right? If we have f prime, what's that going to give us? That's going to give us 1/3 x to the negative 2/3. F double prime is going to give us negative 2/9 x to the negative 5/3. Okay? So all I did, multiply negative 2/3 times 1/3, and then subtract 3/3, we get negative 5/3. So if we plug that in over here, what's x to the 1/3 times negative 2/9 x to the negative 5/3 divided by 1/3 x to the negative 2/3 squared, absolute value. So this is going to give us negative 2/9 x to the negative 5/3 plus 1/3 is negative 4/3. On the bottom, I'm going to have 1/9 x to the negative 4/3. So look at there, the negative 4/3 cancel out, the 9 cancels out, I have negative 2. The absolute value of negative 2, right, because this is all absolute value, is 2. Is 2 less than 1? Nope. Therefore, it does not converge. So that's a little test. If you start playing with one and you think it's not going to converge, plug it in there and see, will that value converge or not? Okay. Now, you've learned several techniques for finding the zeros of function. All right. Some things like x cubed minus 2x squared minus x plus 2, we can find those just by simple algebraic techniques like factoring, right? We can see that this has 4 terms. We can do factoring by grouping. However, sometimes something like x cubed minus x plus 1, there are no elementary algebra methods for solving that. Now, there are some super complicated, higher level algebraic functions or algebraic methods for solving that. So if you want to know what the real zeros are, here they are. Okay. Negative cube root of 3 minus the square root of 23/3 divided by 6 minus the cube root of 3 plus the square root of 23/3 divided by 6. This is ugly, and this is an exact solution written in terms of square roots and cube roots, right? This is a solution by radicals. Problem is, I have no clue how to get that. However, if you plug this into your calculator and then you do Newton's method on this, you'll find that they're pretty close together. Okay? So, if you have any questions about this, maybe not about, don't ask me how to do this, because That I do not know. That is not in this class. Okay, this is not in any class that we teach here. But if you really want to know, come find me and we'll figure it out. But if you have any questions about Newton's method, shoot me a remind or ask questions in class.